By 1956, as I tell people, and they find it somewhat incredible these days, I felt that the pioneering days of digital computers were past in 1956. Maybe it was only that I was tired of them by that time. Perhaps it was that I was now looking for some new frontier. But in fact, the improvement in computers between 1946 and 1956 is probably greater than any decade since. It's been huge, of course, in succeeding decades, but it was a tremendously big step in that decade that we all had a part in. So part of my career has been a willingness to wipe out the past and walk through an open door when there's an interesting one ahead. And that was true getting into digital computers. It was true getting into the air defense system. And then as it began to be settled, by 1956, the North American air defense system was frozen. The contracts were written, the contractors were doing the work, the design was set. There was very little that one could do to change what was going to happen. And in fact, the first installations were ready to be put in place. It didn't seem necessary to pursue that. At least I didn't feel it was necessary that I pursue it. Again, through happenstance, and one of those opportunities, Jim Killian, who was president of MIT, came with some dignitaries to visit the Lincoln Laboratory and just casually in the hall said they were starting a new school of management. There might be something there of interest to me. And that led to about a year of meetings at the houses of the Associate Dean Eli Shapiro and Edward Bowles, who was a consulting professor. We never did figure out where that title came from. And the upshot was that I came to what is now known as the Sloan School. It was the School of Industrial Management at that time. And I had one of those rare, first of all, I had not, going back to some of the questions that Nelson's raised about academia, I had not been in the academic setting. I did not have any faculty appointment. I was a member of the Division of Sponsored Research staff, entirely outside of the academic circles, working on what I would call these real-world problems. And I came into the Sloan School as a full professor, which is not the common career route. With a year to decide why I was there, which is also probably unusual for most people entering academia at this time. And in that process, looked at what probably other people thought I was there for and what I perhaps also assumed in giving some meaning to the vision that Alfred Sloan had in setting up, in giving the $10 million necessary to launch the School of Management within MIT. And he had the vision that a management school in a technical environment like MIT would probably develop differently than one in a liberal arts environment like Harvard or Chicago or Columbia. Maybe better, maybe not, but people of that sort are willing to put $10 million into an experiment and see what happens. And at the time I joined, the school had officially been in existence 4 years, but hadn't really had any links to the technical side of MIT. So I was pretty much the first person to move across that boundary. And people assumed that it would be to work on how business should use digital computers for information processing or possibly to push forward the field of operations research. And I examined these. And I guess on the matter of computers for handling business data, there was tremendous momentum by that time in the banks, in the insurance companies, and among the manufacturers of computers. And I doubted that we would have much influence, at that stage anyway, on what was happening. And I felt we had perhaps done our share in this by our activity in launching the computer field. So that didn't seem of major interest. And as far as the field of operations research was concerned, it seemed interesting. It probably was worthwhile, but it didn't seem to couple to the real world in the way that I would find satisfying. It clearly was not dealing with the big issues of why some corporations succeed and others fail. And
can I just ask, how widely practiced was operations research at that time? I'm sort of interested in maybe ultimately coming back to a question of comparing the progress of that field with system dynamics. So to ground us in, when system dynamics was getting started.
Well, for years, it pretty much was the same thing it was at that time. It had started, operations research had started in World War II by some very able physicists, Bill Morse and here and various people in England, to work on largely the statistics of bombing runs and how you should lay down targets. As far as I know, that was successful and worthwhile. And then it gradually, again, emerged from the military field into the corporate field. And they were working on things like the traveling salesman problem and how to optimize machines in production and things which pretty much were the sort of things that for decades went on. And again, on fragments of the corporate problem, each study being on just a piece of the corporate problem. And it turned out, again, I suppose by a certain amount of good luck, that I had a series of conversations with people in industry, primarily people in General Electric at that time, on some of their problems, what they considered to be their serious problems. And again, as you now recognize, system dynamics starts with a problem. It doesn't start with a system. It doesn't start to, it's not proper to start by trying to model a system, but rather to model what system applies to a particular problem. And they had a problem. They had a problem of a high degree of instability in their manufacturing facilities for household appliances. They might be working 7 days a week, 3 shifts 1 year, and have most of the people laid off, or a lot of people laid off 3 years later. And casually, it was explained by the business cycle that changed demand. On the other hand, they weren't quite persuaded of that, and I certainly wasn't persuaded of it. And the very first system dynamics simulation model was done on one notebook page, pencil and paper computation. Columns for inventory, number of employees, production rate, backlog of unfilled orders, and every line was a week. And the policies that they said they were following for hiring people and managing inventories were used each week to determine what the condition of the system would be based on the situation the previous week. And immediately, by the time I got to the bottom of the page, it was clear that even if orders came in at a constant rate, they would be generating that instability that they saw. Those of you that have seen and played the beer game will recognize that immediately. The internal instability that can be generated in an inventory production distribution system. That became my first article in the field, published in the Harvard Business Review. I think the title was A Breakthrough for Decision Makers, something of that sort, and is now available in chapter 2, I think, of my industrial dynamics book. And that launched the idea of being able to go into a social system, a corporation, and capture the essence of the feedback structure and how decisions were controlling events. Yes?
I have a question about that very first simulation. I haven't studied electrical engineering to the depth of some others, but the tools and the diagrams in electrical engineering are not exactly the same ones that you developed in system dynamics. I mean, the stock flow diagram, as far as I can tell, you invented. I mean, there's things in other fields of engineering that look sort of like it, but they don't have that, in some ways, that simplicity and that basic notion that there's just stocks, just flows. So I guess my question is, did you come up with that then, and how did you come up with that? And I'm just very curious about the process of going from electrical engineering, where you have a finite set of elements that you typically use, whether it's blocks in your block diagram or capacitors or resistors, to this in some ways more basic and more fundamental representation of the system of just stocks, just flows. Because going from a capacitor to inventory doesn't seem like an obvious mental leap to make. I don't know if it was some time ago, but I wonder if you can remember what led up to that.
Well, that very first hand simulation was drawn essentially out of the real world. They were talking about inventories. They were talking about employees. They were talking about production rates. They were talking about order backlogs. Three of those, order backlogs, employees, and inventories, are what we now see as stocks. And so that first simulation modeled it as it was seen. It was probably a little later, but not much later, that we began to realize the fundamental nature of that formulation. There is a book, the citation escapes me at the moment, in psychology by a man that I think was on the staff faculty here, in which he defines the stocks and flows in one's mental condition, one's mental attitudes, how there are certain attitudes you have and there are certain forces that cause those to change. A very clear statement of exactly this kind of idea. Now, I think one of the most important things in the underlying methodology of system dynamics is this idea that it's the integrations, it's the stocks that matter. It's the integrations that produce the dynamics. Because if an integration changes the time shape of an input. If you integrate a straight line, you get a rising line. If you have an input which is constant, the accumulation, the integral, is steadily rising. If you have a constant flow of water into the glass, the level of water continues to rise. If you have an input that itself steadily rises, you get, I believe, a parabola. You get a stalk that looks like that. The stalks are fundamental because they are the creators of dynamic behavior. And it was Gordon Brown, my mentor, who explicitly said to me for the first time, nowhere in nature will you find the process of differentiation. That is a very important thought. You see, dynamics down through the years and throughout engineering was taught and still is taught in the context of differential equations. This, I personally feel, is one of the great disservices that's ever occurred to understanding. Because mathematicians have a certain amount of difficulty defining a derivative, and I would assert that the reason for this is there is no such thing. Nowhere in nature does nature take a derivative. Nature only accumulates. Nature only integrates. And I leave it to you to find a place in nature where a derivative is taken. People will come back and say, well, a speedometer is giving you velocity. But if you look inside it, it's got an integrator in it. Every instrument that purports to measure velocity lags the real world. It has some sort of integration process in it because it has to make a comparison between the present and the past in order to arrive at a velocity. And so it goes. Wherever you look, if you look closely enough, you will find that the basic dynamics of behavior revolves around integration. Now, as soon as you do that, dynamics becomes remarkably simpler. In the kindergarten level, in one of the schools of New Jersey, the kindergartners start out by picking in their environment which are the stocks and which are the flows. The water in the glass is a stalk. The water in the lake is a stalk. What people think of me is a stalk. So you begin to get the fundamental nature of the structure of dynamics understandable at the kindergarten level. And by 5th grade, they're doing actual computer simulation modeling, which my engineering colleagues would often say is impossible until you get to graduate school here. And the reason for it, I think, is this alignment with the real world and the nature of the way in which dynamics is represented as feedback loops and as stalks and as rates of flow into those stalks. And initially, system dynamics dealt with what you might call the hard and measurable variables like inventory and employees.
While we're still on that very first simulation, you said by the time you got to the bottom of the page, you had shown that those very stocks and feedbacks were able to generate the instability that was true in the real world. Did you know that, or did you expect that before you went through this simulation, or was this very first simulation an example of the model actually generating that kind of insight? Today we know, Scott alluded to earlier, that that fundamental structure is capable of generating oscillation. Was that something you discovered then, or was it already known in engineering and you've just sort of induced its...
The answer to that is uncertain. I don't think I knew that it would happen, but I obviously had enough of a suspicion to be worth computing the page. In other words, there was something there in the background that suggested it might be worth carrying through a page of computation. But I don't think that I was actually aware of the fact that it would generate the oscillation. I certainly wouldn't have predicted exactly what the periodicity of that computation would be, or whether it would be stable or unstable. That, I think, would be a result of carrying through the simulation. But obviously, to set up a hypothesis, after all, that worksheet with its columns and lines was a hypothesis about behavior. It was a theory, as we talked about before. And then you simulate it, you compute it through, and you begin to now say, and is this behavior anything like what you're seeing in real life? And once you ask that question about a distribution system, there are all kinds of places where that instability appears. In automobiles, in textiles, in any multi-stage distribution system. So that was the first generic structure that I had any hand in. Relatively simple and repeatedly to be seen in the real world.